Hi to everyone joining us. We're just going to give it a few moments. I can see we've got participants joining very quickly. So let's just give it a few moments for everyone to jump on, and then I will be back with our introduction to kick off today's session. Right, I see there's still more people coming through, so we'll just give it another moment or two. I see a few familiar names joining back in for today, so thank you for those that are joining us again for this webinar that have been on a few in the past. So thank you to everyone for joining. I think I will get started then with introducing today's session. Thank you for joining us. My name is Brandon Ward. I am Director of Reed Exhibitions Mining Portfolio. The ongoing webinar series is brought to you by Reed Exhibitions, comprising Amex, QME and WA Mining. And just a point I would like to note is that QME has been moved from July this year to the 22nd to the 24th of September in Mackay, and WA Mining has moved from October to the 11th to the 12th of November 2020 in Perth. I would also like to thank the sponsor of today's webinar, Optica Solutions. For more information or to get in touch with Matt and his team, please visit their website, optica.com.au. If you are watching this as a recorded session, please see the links in the description below for further information. This presentation is part of an ongoing series of videos and webinars. We will present both live and pre-recorded sessions on a broad range of topics. If you're interested in attending future webinars or one of our events, again, please visit any of the links listed in your confirmation email or visit any of our event websites, Amex, QME or WA Mining. For today's session, please leave questions for the speakers in the Q&A section. This is going to be a live Q&A at the end of today's broadcast. So please, we do encourage you to populate those. We have the panelists will be waiting for us at the end to answer any of the questions that you may have. So just click the Q&A button on your screen and you can populate that throughout the session or at the end. I'm now pleased to introduce the session chair for this webinar, Rick Gross, who's a fellow of the Institute of Company Directors in Australia and Optica Solutions Executive Chair. Rick is a former CEO of Meds Ignited, one of 6 industry growth centres at the core of the Australian government innovation policy, which developed Australia's SCP for Australia's mining equipment, technology and services sector. An industrial engineer by profession, Rick has been leading organisations to transform and accelerate growth for over 30 years. He is CEO and MD leadership. He has had CEO and MD leadership roles across FMCG, infrastructure, B2B industrial, mining equipment, mineral processing and technology sectors, all in early stage growth and ASX listed environments. With extensive global networks, Rick has a particular focus in Latin America, where he is also the chair of TI Mining, a Chilean company focusing on mining 4.0 digital solutions. Rick will be joined by an expert panel comprising Eliza Jordan, who is a domain expert and consultant, and also Matt Schneider, who is the founder and managing director at Optica Solutions. I'm now pleased to hand over to Rick and the team for today's webinar.
Good morning all. It's a pleasure to be here as part of the WA Mining webinar series. Thank you to Reed for their support of the industry and their commitment to open debate, education and recognition of the importance of the resource sector to Australia and in particular to Western Australia. I would also like to take this opportunity to thank the speakers for providing their time to this event. We have an exciting session today where we'll be discussing the 5 most powerful data science techniques to unleash value in your resource project. There is much to talk about machine learning, AI, and how data science will solve all manner of problems. Our aim today is to provide you with an introduction to data science, its history, and its benefits to industry, the most relevant data science techniques, the types of problems that can data science address today. Then we'll go on to talk about the various stages of a project life cycle and the various opportunities to leverage data science through each of these stages. Next, we will talk about the 5 most powerful data science techniques and where to apply them. I promised it won't be all about machine learning. Finally, we will talk about the secret sauce that really brings out the true value in data science. And at the end, we will have some time for some questions, and we certainly welcome those. Okay, so without any further delay, let's begin. Matt, over to you. What is data science?
Thank you, Rick. Data science at its core is an interdisciplinary field that uses scientific methods, processes, algorithms, and systems to extract knowledge and insights from data. The term came into existence in the late 1990s and has gained lots of momentum ever since. The key to success is to create a bridge between the data and your decision making.
But Matt, using data to build predictive models isn't new. Optimisation isn't new. We've done it back in the 80s with statistical regression models and linear programming. We used data for process control. The whole era of Six Sigma was all about using data to make decisions and improve processes. So why is data science any different? What's the difference? What's the change now?
Rick, that is a great question. Too often we get caught up in the hype of ML and algos to stop and think. Perhaps all the fear for data science and AI is because people aren't aware that it is based on fundamental theory that was developed decades ago, and there isn't some weird, magical, sinister force behind this. It is really just maths. You are right. A lot of what data science is today isn't new. What is new is the tendency to think up weird and wonderful names for stuff. Most techniques are small variations of an older method that can just do things better, faster, and at scale. But in essence, 2 major changes happened from the time that computers enabled the use of statistical software to learn from historical data. The first is a change in the fundamental theory behind how statistical models or mathematical models learn from data. That happened around the early 90s. This new theory, described in the book Fundamentals of Statistical Learning Theory, gave way to a new family of model structures, network-based structures. And this is the birth of neural networks and support vector machines, the AI what we're looking at today. This also brought a shift in the focus of what analysts did when they build models. In the past, much effort went into reducing the dimensionality, which is the number of variables, used in the problem. If not, the statistical models couldn't be solved. And this is known as the curse of dimensionality. The new structures can now handle as many dimensions as you like, so lots more variables. So the focus went into finding more complex model structures to find suitable solutions, and thus more complex problems could be solved. For the first time, problems like character recognition, face recognition, and human gene arrays could be tackled. But what limited this new paradigm to make big waves in industry was the limit in compute power, and in particular, memory. Then came the mid to late 2000s, and computer hardware caught up. Enter the massive parallel processing architectures, AWS for example. Suddenly, compute power became less of an issue, enabled the use of much more complex model structures like deep learning, and the focus went from tinkering with the algorithms in the background to solve problems using subsamples to using all the data at once. With this advent, more complex problems could be tackled like natural language processing, video analysis, object recognition, and autonomous systems. But the drawback was this compute stack was expensive, and thus wide adoption across the industry was limited to the select few. The advancement of cloud compute opened it up to the masses. Cheap, on-demand, high-end compute is available to even the smallest players in the market. What we see now is a shift from continuously building an internal compute infrastructure to the rapid consumption of data, ML techniques, and insights. In all of this, the traditional regressions didn't become obsolete. In fact, they got a massive boost back into popularity, and unfortunately, often with weird names to go with it. And therefore, we have a plethora of possible ways to approach a problem, which is a real challenge, but they are fundamentally still the same techniques of old.
So it sounds like in order to use data science efficiently, you need to have certain processes in place that allow for data collection and interpretation.
Yes, Rick. And sadly, without those processes, the whole project must be started from scratch. You need to have the right data from the right source at a good quality for your results to make sense. If you put garbage in, you will get garbage out. The data in the data warehouse or data lake is typically relevant for BI reporting or basic diagnostic analysis, but not answering the more complex questions, particularly when it relates to machine learning. The data scientist needs to understand first and foremost the business question and then transform that into a mathematical equivalent. You're looking to create a bridge between the data and the question that needs to be answered.
Excellent.
This slide highlights a simple view of the mining value chain and the mining life cycle with the various functional areas. The specific opportunities are many, and I will now share with you some of the most common challenges that we are seeing today that can be addressed by using data science. Drill location, hazard ID, deposit quality and sizing, equipment design and selection, mine plan options, blast locations, production optimization, predictive maintenance, debottlenecking, port operations, fuel and energy consumption, decarbonisation, pricing models, shutdown planning and investment strategies, to name a few. I now look forward to Elsa introducing us to a selection of data science techniques available to the intrepid problem solver to answer these questions.
Thanks, Matt. The mining industry is clearly set for some big changes. It is exciting to see how data science can help us take on some of these challenges. Today, we'll take a look at 5 of the most valuable data science techniques with which you can build bridges between your data and the decisions that needs to be made. Firstly, there is digital value stream mapping. Value stream mapping is a foundational approach that digitally connects data and information in a value stream. The next technique is what is called value driver trees. This is a technique used to understand the range of outcomes that millions of possible scenarios can produce. The third, machine learning, and fourth, optimization, of course has a place in our list. These techniques have done some heavy lifting in the past and will continue to do so. The final technique is what we call the golden thread. This is a technique that connects all of the above to generate value vertically and across the mining life cycle. Let's get further into detail for each. Rick, you have some extensive background in value stream mapping and Lean Six Sigma. What is it about digital value stream mapping that got you so excited?
Thank you, Elsa. I think most of us are familiar with value stream mapping as a lean thinking tool. The slide in your screen shows a typical example. A value stream map typically illustrates the flow of materials and information as a product or service moving through a process. Value stream mapping is applied with the single purpose of eliminating waste. Waste is anything which does not add value to the overall process. The process is always looked at from the customer perspective. It's a very customer-centric approach. As we all know, value stream mapping is a tremendously valuable tool for improving a process and well suited for a broad range of industries and processes, and also starting to find its way into the mining industry. In fact, I encourage you to Google the Lean Mining Institute, which is a rich source of information on this particular topic. Creating a value stream map of the current state of your process helps you to focus on areas of waste, such as excess inventory, non-value-added item, debottling, etc. It is not an easy undertaking, but making a good value stream map is a great way to help everyone involved understand and see where improvements can be made. It is a great collaborative approach of gaining a shared view across the whole value chain. Now let's talk about a digital value stream map. A digital value stream map with access to basically unrestricted data can take this process to another level again. A digital value stream map has the capacity to capture all the value stream or flow with also capturing the data in context. Imagine a library where every object representing all the parts of a value stream, whether it be a machine or a resource or a raw material or an energy source, etc. Each of these objects will contribute to the digital value stream via 3 different types of data. If you look at the table, you will see that these types of data are distributed as follows. There are object attributes of fixed data, such as nameplate capacity, footprint, maximum energy rating, etc. There are object attributes that are adjustable, such as flow rates, process settling rates, etc. There are object inputs, such as data from multiple IoT devices. We might have inputs from algorithmic models that are providing optimization data or forecasts from future temperature or future weather patterns. The options are varied as your imagination. And lastly, there are the object's outputs, which will include process outputs, waste, heat into the environment, etc. Accordingly, a digital value stream map provides enormous insight into an operation. It can be live and dynamic. It can be a set of static data able to change variables and or set constraints to explore multiple variable scenarios. The view of a digital value stream map can be seen from multiple contexts. It may be centered on an optimization loop around the crusher, or we may be evaluating water consumption across the entire flow sheet. A digital value stream map provides an ability to bring constraint-sensitive scenario evaluations. Digital value stream mapping is highly complementary to current value stream mapping practices, and in particular to well-developed lean cultures who are very adept at evaluating, assessing, and innovating in a collaborative manner across the organization and across the supplier partner networks. The additional potential insights that can be gained by deployment of a digital value stream map are extensive. This slide shows a base metal primary circuit from run of mine to final filtration and tailing storage. Based on our previous slide, you can now appreciate the 3 types of data available for each object in this overall flow sheet. The data can be live and or can be historical. Value can be unleashed across each single silo, across silos, across multiple silos, or across the whole value chain. We'll speak a lot more about the whole value chain later on. Digital value stream mapping can assist with simulations, what-if scenarios, debottling, consumption constraints, and link to any type of decision. A digital value stream map is a data-rich complementary tool to traditional value stream mapping and serves as a foundational tool to drive continuous improvement and innovation across any organization.
That's right, Rick. And of course, value stream mapping flows very nicely into a particular type of modelling called value driver trees. A value driver tree is a visual representation of a business model that links a business value, e.g. profit, to a set of drivers. Any variables that can affect the value, for example, revenue and costs. VDTs were first invented in the 1920s by DuPont, who used a visual model to define the return on investment. Now, value driver trees, or VDTs, are models that digitally represent a process map or a value chain map. So these would traditionally be applied after you've done your value stream mapping. Since at this point we've already worked out what the chain is, where the value is in that chain, and what the paths along the chain will look like, and top it all off, you already have the metadata and information of those assets to use within the modelling. The difference between VDTs and value stream maps is in the way we use them to draw inference. With VDTs, we can run what-if scenarios to our heart's content. The technology advancement allows us to run an unlimited number of scenarios, so we can test every possible outcome of a very complex system, a process map. It's a flexible planning and analysis tool, which has endless possibilities of solving problems across the mining life cycle. One such example is in debottlenecking. Here we have a very simple mine VDT describing a mine-to-mill process. The question is, what is the minimum number of trucks required in the circuit to fully utilise the mill? Whilst this seems like a simple scenario, we've identified more than 2,000 variables impacted on the operations, and we consider this to be a small VDT. In the first scenario, the number of trucks was 3 and the tonnes moved was 21,600. For each of the scenarios, we wanted to see how the number of trucks affects the number of truck tonnes moved, along with the other control and uncontrolled factors. The 20th scenario had 2 trucks with a total of 14,400. And the 300th scenario had 4 trucks with a total of 16,700. Now this driver tree is just one part of a much bigger tree in which we ran over 300,000 scenarios, varying factors across the VDT in minutes. After analysing each part of the VDT, we could see that having more trucks did not necessarily equal more tonnes moved. There was clearly another limiting factor which is preventing us from moving more dirt with these trucks, and after further analysis, this was identified as a truck throughput problem. We could then take this into account when analysing 300,000 scenarios to find the best possible sequencing.
Let's talk about machine learning and the power of learning from the data we have. Elsa, the other day you mentioned there are 3 different types of machine learning methods. I always thought there were only 2.
Yes, there are indeed 3, Rick. It is supervised, unsupervised, and reinforcement learning. Supervised and unsupervised learning is the most widely known methods and used, but reinforcement learning is a bit of a hybrid of the 2. I'll focus today on supervised and unsupervised because I think it is important to understand the difference, as they are fundamentally different methods and applied to fundamentally different problems.
How so?
Well, supervised learning implies that there is a supervisor or a teacher, one who knows the right answer. Here, the teacher isn't a person but historical data that captured the desired outcome. We can also use this teacher to judge the accuracy of the model and determine how stable it is. In contrast to supervised learning, unsupervised simply means that we don't have that teacher or the desired outcome. So technically, we don't know what is right or wrong or how close to the right value we are. What we can do is to look for groups of similar data. The best model will be the one that distinguishes more clearly between the groups.
But how come there are so many different machine learning techniques out there?
Well, Rick, that has to do with a number of things. One is the nature of the teacher data, and the other is about the subtle differences in how these methods penalizes for error and control complexity. The type of data will determine whether we are dealing with a classification, regression, or forecasting problem. In classification, we are predicting discrete values, like yes, the pump will fail, or no, it won't. In regression, we are predicting any kind of real value, like how long is it before the pump will fail. In forecasting, we also deal with real values data, but here time forms a big part, and the predictions are always into the future. In unsupervised learning, there are also 2 types, clustering and principal components. In clustering, it is all about finding the centroids of these groups, whereas principal component analysis look for latent variables.
Oh, I get it. So depending on the type of question and the type of data, we would use a different machine learning method. Can you talk through some examples of where you have seen this generate value for your company?
Of course. Let's start with unsupervised learning and look at clustering. Before I show examples of its use in the resource industry, I'll quickly describe how it is used on customer data, because it is something we can all relate to. Essentially, what we do is to take all the information we have about our customers, like which devices they have, what they buy, how much time they spend online shopping, and so forth, and then use clustering to look for groups with common behaviors and characteristics. A lot of work will go into understanding exactly what characterizes a group. This is where segment names like Dinkies, double income, no kids, or the experienced risk takers, or the keep it for the rainy day savers come from. Once this is known, we can then design more targeted marketing campaigns, better products and strategies around what would be best suited for a particular segment. Interestingly, clustering can also be used to detect things that doesn't fit in the groups that we have identified. In the resources industry, the same technique is used to find abnormal operational behavior. Large, dense groups of similar operational data would typically represent normal operating modes, but then we use this information to find the odd stuff. Data falling outside the clusters of normal behavior can be considered as anomalous, and often these can be linked to pending failure modes. The power of clustering is often magnified when used in conjunction with other techniques. This use case is one of the neatest applications of such a combination I've ever seen. At a utilities company, they wanted to understand water usage in households. They wondered if, with the use of data science, they could actually detect from the flow pattern of a single flow meter when somebody takes a shower, flush the toilet, do the laundry, or water the garden. First, the total flow was disaggregated to show consumption patterns. These were then transformed to extract some features about the signal, things like duration and flow rate. Clustering was then applied to group similar signals together. When they looked at what these clusters contained, they found groups of short bursts of small usage, groups of longer high demand usage, and so forth. To validate the clusters, a family volunteered to record time and duration of every water usage in their house. This helped us to confirm that the short, small bursts were typical of flushing a toilet. Longer, high volume usage were typical of taking showers. Armed with this knowledge, the utilities company could then make inferences about water usage in various neighborhoods. Classification is a very common supervised machine learning technique. It addresses a wide range of problems. One often showed is whether a piece of equipment will fail or not. But I'd like to talk about another example that will make a big difference in how the resource industry manages their aging assets. Millions are spent every year to inspect pipelines, structures, and equipment for signs of corrosion to prevent loss of containment or structural failure. Deep learning is unlocking the value of image data we have in our archives. Without telling the model what characteristic features to look for, the deep learning model, in this case a convoluted neural net, learns what portions of an image to classify as corroded or non-corroded. Yes, it took a lot of time to label enough training images for the model, but once this exercise was done, we can pass thousands of images through a deep learning model and be able to identify where there is corrosion and where not. Combined with this location information, asset managers can generate a heat map of where the problem areas are, and even over time, track the progress and speed at which corrosion is happening. The next example is a twist on the classical regression model. Here we have used random forest models to predict the remaining useful life, or time to failure, for various types of equipment. In the image on the left, we can see how the model uses a subset of 16 historical failures to learn from and test on 3 historical failures. On the right, operations can now plan and prioritize maintenance activities based on the predictions of how much time they have before the equipment is likely to fail. The final supervised technique is forecasting, also known as time series analysis. I'll be very brief about it, but that is no reflection on its importance or usefulness. Forecasting is used all across the mining lifecycle. For example, it is used to budget long-term cost projections of labor and construction costs over the course of a major project. It can also be used for short-term planning, like playing in the spot price market.
So Elsa, the fourth technique is optimisation. You are very adamant that this is a technique in its own right. Can you explain that, please?
Well, Rick, it is its own technique because it addresses a very different problem and is approached in a very different way. To explain this, I will use the problem of washing dishes. There are multiple ways to get the dishes clean. You can wash by hand, or by stuffing the dishwasher as full as possible, or by doing it a bit more organized. Depending on your goal, speed or cost, and how much you are willing to compromise on how clean the dishes should be, you will pick one. You may have the dishes the wrong way around and have puddles in it at the end, but you can't have the dishes obstructing the rotating arm at all. The key part is to understand the goal to maximize or minimize, what you are willing to trade off against, and how hard or soft the constraints are. The bottom line is the best configuration will get as much as possible in and still get everything clean. Depending on your goal, there might be different outcomes. That is the power of balancing the trade-off techniques. Transportation and logistics is an important part of the mining life cycle. In this use case, we look at improving the efficiency of ship loading. Data science addresses two aspects of it. One is about finding the best configuration, and the other is the fastest sequence or order in which a ship is loaded. With the best configuration problem, we have to ship a set of containers of varying size and weight. The best solution will have the ship in ballast, minimize the waste space, and meet some other requirements. In the image on the left, we see the optimizer produces various solutions, but only one will have minimized the space used. In the best sequence of events example, we need to load ore of different grades onto a ship as quickly as possible. Various routes can be used to get the ore from the stockpile to the ship. Some routes may share equipment, like stretches of conveyor belts, the stockpile ore reclaimers, and the ship loaders on the wharf. We can see at the bottom right image, the best sequence saves 1 unit of time, which could just make all the difference in getting more shipments through.
But Matt, what about the fifth one? The golden thread. I mean, really, how is that a data science technique? It just sounds like putting everything together.
Well, Rick, it is actually a technique. It's a way of looking at all decisions across the whole value chain and stringing them together to leverage value stream data in multiple possible ways. We can interact with the digital value stream to discover all the decision loops, and by leveraging the many techniques we have shared with you today, we can identify what we describe as a dynamic golden thread. This is the path that will deliver the optimize based on the current constraints you're experiencing. So the golden thread can be found for a subsystem, a whole of system, or a system of systems. From a systems of systems theory, the ultimate objective is to dynamically link your digital value stream with the data science capability and high-end compute available today. We are effectively daisy chaining all your algorithmic models to provide you with the best decision options, augmented with the most relevant data. The same daisy chain can provide powerful simulation capability. In this sense, the golden thread should be something that all organisations should be pursuing if they are to remain competitive and relevant in this new world. Here is an example of the golden thread applied to port operations. In this case, we were challenged by our client as to whether it was possible to create an autonomous port. To get an autonomous port concept to work, we took a systems of systems approach. We initially used an unsupervised machine learning model to dynamically identify from all the historical operational data the core relationships between objects, their attributes, and connections to automatically create a digital value stream map. We then used value driver trees and their what-if capability to model millions of scenarios and overlay this insight of the digital value stream map to understand the types of algorithms required to ultimately construct a self-organizing golden thread, and in the process, defining the decision sequences required to create an autonomous port. It's important to realise that only 2 years ago, this was not possible. The computing capability required was simply not available for general commercial applications. Today, this power is easily accessible to any startup. This is an excellent example of all the techniques coming together and how, with high-end compute capability, just about anything is possible, provided you have the secret sauce.
So, now that we have a fuller understanding of what is data science, and we're all more familiar with the 5 most powerful techniques, what is the secret sauce? How and what is required to ensure we accelerate the value creation? What is the single bullet that will give us instant success? Well, I think in the midst of all of this technology, we're all guilty of wanting a simple solution to solve our problems. We look at AI as the answer to organizational challenge, to make our jobs easier, to reduce repetitive, boring work, to unleash this hidden value. But extensive research and experience gained by many companies show that technology is only 10% of the solution. Process becomes more and more critical to the progress of realizing value from data, but only represents 20% of the story. It is people, our teams, our operators, our organizations that ultimately will leverage the tools and enabling capabilities that data science and technology stacks or technology platforms can provide. I referred to earlier to the power of lean cultures, highly collaborative organizations well aligned to share a purpose with processes that support the development and capture innovation where the innovation process is the core competency. The secret sauce should not surprise us. It's people. Today, cloud computing, cloud architecture, the convergence of IT and OT, and the explosion of IoT devices are providing unprecedented access to data. Today, data science and technologies can turn data into insight and information faster than ever before. Today, data science capability is no longer a separate function. It's an intrinsic capability across all functions. Today, resourcing your talent with the right tools, the right processes, the right culture will unleash the value creation in your business. So why do we encourage a lean culture? As management guru Peter Drucker said, the essence of management is not techniques and procedures. The essence of management is to make knowledge productive. Data science and today's technology stacks gives us unprecedented amounts of data. What we have shared with you today shows how to structure your data in context. The techniques we have shared with you, when applied to the right types of problems, will provide unprecedented insights, information, and knowledge. You will have the ability to codify and capture your current best practice until your lean core competency takes you to your next current best. But the winners will be, as Drucker said many years ago, those organizations that make knowledge productive. And I would also like to add, make knowledge productive as fast as possible. Thank you.
Thanks, Rick. Thanks, Matt. Thanks, Elsa. I'm sure everyone will agree that was really insightful, and I'm sure you're only just touching the surface there. I'm sure there's a lot more behind what you were discussing today. So again, I would encourage everyone, if you've got any questions, please now start populating the Q&A. I know we've got a couple of regulars that have joined us today, so we're sure those questions will come through shortly. There are a couple that have popped up though. Matt, you talked about the golden thread. How is this different from digital twins?
I think it's important to understand digital twins follow a life cycle. So they're very much around the reflection of an organisation or a structure of an organisation. And you can create a digital twin of a crusher or a process plant. Where we're focusing within the golden threads, it's the ability to actually link all of these different elements together. So you might have lots of different digital twins working together. And the trick is actually being able to link them together in a systematic way. If you can do that, then you can create a really powerful way of making decisions, etc. Elsie, do you want to add anything to that?
Well, that's actually, no, I think that's a very good description. You can get digital twins that actually try and represent a physics model as close as possible for a piece of equipment, or it becomes a more of a just a mathematical representation. So there's different ways to use digital twins in a bigger context.
Excellent, thank you. There's another question here, and I'm just trying to get my head around it a little bit. It says, how important is industry to data scientists? And I wonder if that question means how important is the mining sector to data scientists, and how appealing is it? Would that be accurate?
I think so. I think in the world of data science, there are many areas that that data science can be applied to. I think one of the interesting things, Brendan, is that the resource sector presents data scientists with some of the most complex problems because there are so many unknown variables, and because there are so many variables. In actual fact, in major industry, we do a lot of work through lean thinking, for argument's sake, to actually remove the variables. And the more that we can control the inputs, the more that we can control the process. Whereas in the mining industry, we are at the mercy of the actual front of mine, the actual run of mine material that is changing constantly. And so therefore it creates some really challenging problems for data scientists. Elsa?
Yeah, and I think what is really important is the industry is important for us as data scientists because it challenges our creativity. It challenges our knowledge about what the data is, how it's presented, how it was actually collected. And we have to find that reality married with a theory on the other side, or a technique that makes some assumptions. So that creativity of how you get your theoretical, technical maths working in something that's real is actually the thing that makes our data scientists become better. If we keep in the theoretical world, we always will just model the spherical cow if we talk about that. But the industry makes us become real. And that's one of the things that's challenging and that excites us.
Excellent. We've got a few more questions coming through here now. So I'll go to a question from Vivek. And Vivek, I apologise, I'm not going to try and pronounce your surname, but thank you for your question. Vivek asks, can we use a critical path method with resource leveling and smoothing that we use in project management for this golden thread model?
You want to take that one or?
Yeah, you take it.
Okay. It certainly is a technique that we have used in order to sequence our events. The challenge is really, when you're looking at golden thread type approaches, it's about understanding it's a dynamic system. So when you're looking at critical path analysis is very much it's almost like a linear stepwise function.
Yes.
Whereas what we're finding in golden threads, particularly in the mining industry, is it's a very dynamic system. And you've got to be able to understand that the system itself is always moving. And it's the ability to understand that your constraints do move and your bottlenecks change, theory of constraints come into play. So it becomes a very complex systems problem you're trying to solve. And that's very much where where the techniques have to be focused.
Thanks, Matt. And I think there was just a follow-up to that from Vivek, and then we'll move on to somebody else's question. But he also asked, with IoT, we can get lots of data. Is there any way to segregate the data with reference to mining and quarrying?
Do you do that one, or do you want me to do that?
I'm not sure I understand exactly what the...
I think I think the question is about segregating the data from, you said from mining and quarry, is that correct?
That's right, yeah.
I mean, really, the reality is that IoT data can be segregated in multiple different ways.
Yeah, it really comes down to the context. So if you saw, with Rick's conversation around the objects, etc., that gives you the ability to understand data in context. You understand where it's coming from. So IoT devices give you a source of truth. And then you look at data provenance. And then from that, you can understand the context. And that's really how you can classify your data.
And Brendan, just going back to Yvette's previous question around leveling of resources in a critical path, fundamentally, that's a really good example of actual creating constraints. A constraint in that particular case happens to be resources, and my critical path can actually shift by the amount of time that I have available to complete different tasks, yet not compromise the end delivery date. But in reality, in any project, of course, and in a production system that is live, the number of variables are enormously large, and the ability to be able to have a digital value stream map is fundamentally that we're creating that ability to be able to shift and measure the output or the input or the outcome by any of the variables that we're looking at. It could be resources that we're looking at. How do we actually manage to maximize our productivity based on the resources that we have available, or people that we have available? Or we may be wanting to measure now, water happens to be a significant constraint in this project. So how do we optimize the NPV of this particular project, but minimizing water consumption? And so therefore there may be some compromises along the lines of what Elsa said, where we're prepared to pay more for a particular process or a particular bit of equipment, but that equipment uses a lot less water. And in the context of all the other variables, we end up with an optimized solution. So critical path is kind of linear within certain constraints. This gives it the next level of power, so to speak.
Great, thanks for that. And we've got another question here from Kelly Oster. So thank you, Kelly, for your question. Kelly asks, can you give some examples of how these techniques are used in mine remediation and provide environmental benefits? Good question.
So certainly what we've seen as part of mine closure planning has been very much around taking a golden thread approach, where we look at the sequencing of all of the activities to make sure that they're actually structured in an appropriate way. Then you move into understanding that you're dealing with an environmentally complex system. And so what you start looking at is bore field management, remediation of soil, soil lithography and structuring. And then you start looking at the regrowth strategies against weather patterns. So you start actually building out these simulations models to understand how you sequence the events, and then make sure that you've got the right instrumentation in place. And then ultimately, we're very much focused around layering in all of these activities to make sure that you can bring our mine back to as part of the mine closure process.
So Brendan, in that context, Matt is highlighting the very specific data science capabilities that can be used and is capable now. One of the challenges in the industry is that historically we've kind of left mine closure planning right through to the last 3 or 4 years. And part of that is the challenge of actually trying to understand the implications and the benefits of actually starting earlier. And so taking this golden thread approach and bringing the capability that Matt spoke about provides us an opportunity to start to measure the MPV, the real MPV of making these decisions earlier and planning more proactively at a much earlier stage in the project. So it's a link of the ability to be able to do what really the mining culture wants to do, but it's been challenged because of its ability to be able to see the actual commercial outcomes.
I think also on that one, Rick, the ability to run scenarios becomes incredibly important, because you're able to run different scenarios to understand the implications. And then what that allows you to do is effectively scenario out all your different options, find the most pragmatic option, and that actually helps with your decision making.
Fantastic. Some more questions still coming through. Shramel, thank you for your question. Shramel asks, how much, I think he's talking about either cost or volume, but how much and at what point should a business invest in data science?
Ooh.
I think we will all want to have a go at answering this question. As you know, Brendan, I'm heavily involved with startups in this world. I think that we're entering a space where high-end cloud architecture and compute power is creating enormous capability for innovation. I work closely with the Australian Space Agency, and Australia's spending a lot of money in developing satellite capability to again be able to link through Industry 4.0 into all the IoT devices. So my argument would be that if you don't have a data science stream to your innovation, you are in actual fact running the risk of being left behind. And with all of the, everything that Matt and Elsa shared today, that capability is accessible to startups today. And you'll find that AWS, Azure, all the big players are actively encouraging startups to leverage their capability, and you find them very friendly to speak to be able to accelerate innovation. Matt?
I think, in a mining context, certainly work that we're now doing is we're now collaborating very much in early stage projects, where we're able to use some really amazing techniques to fast track understanding of the ore body, understanding of your feasibility. We're seeing the ability to do feasibility, equipment selection, radically changing. Literally, instead of taking 6, 12 to 18 months, being done in a lot shorter timeframes. And what we're also finding is that the organisations of the future, particularly with autonomous vehicles coming online and all the smart equipment available, is radically changing how you're going to bring mining operations alive. And I think particularly with greenfield sites, the ability to be innovative, to really leverage the technology, to leverage data science techniques, will create an absolute paradigm shift in how these companies will run the mines of the future. And the earlier you start, you set your culture up properly. And to Rick's point, the secret sauce is all about people. And so you get a digital culture started as early as possible. You get people to be data aware, data literate, and away you go. And it's not about having high priests and high priestesses doing data science. It's actually about empowering an organisation to be data aware. And certainly where we've seen organisations do that, the value creation has been transformational.
Yeah. So being the data scientist in the room, one of the things is that you need to get the fundamentals right, the way that you capture your data, the way that you manage your data, the way that you have your people use the data, and bringing this capability on early, and even if it's just one person, to bring that insight into the way you set up your organization and your processes will really help you in the future, because there's nothing worse for a data scientist than just get data thrown over the fence and there's nothing we can do to make it better. So it's getting the foundation right as early as possible.
And one final comment on that, Brendan. I think the really important thing to realize is that the innovation comes from people asking themselves, what could I do if I had that bit of information? If I wanted to innovate, what could I do to actually innovate, and what information do I need? And what you'll find is that data science will help you find that information, will help you find that insight. So the innovation doesn't come from data science. Data science is a tool that we use once we figure out what is it that we want to do. And what happens today is that what you want to do is so much more accessible than what we would have thought of 10, 15 years ago.
Great, thanks guys. That was well answered. I'm going to try and make sense of that. I've got a curly, well, I don't know if it's curly, but it's long. But it's from an anonymous attendee. So thank you to whoever submitted this. And I apologize if I missed the mark, but they did want to set the scene and set a bit of context before the question was asked. So see if you can help me on this one. So the context is, it seems that a lot of the data science and big data and smart data that may or may not in any event be the desired outcome of all of this for the Industrial Revolution 4.0 is triggered by the increase as to what the presenters have stated in computing power, firstly, and secondly, the bandwidth, including flow meters, and clearly the deployment of 5G to get the data in real time, which obviously leads to the secret source. So the question that they've posed is this, while you perhaps try and get your head around that, is all of this, including the Chilean digital twin showcased last year and also in the webinar a few weeks ago, and many examples subsequently, all seems very focused on the mining aspect, broadly speaking, mining methods, be it open cast or underground, and deep mining and haulage. Why has this data aspect within the mineral extractive industries been less focused on the segmented and in some ways more technically demanding mill feed? Sorry, I'm trying, the question's quite difficult to read. Mill feed is correctly graded, sized and shaped into the mineral process circuits, and therefore focus on this element as it's clearly ultra critical. Please advise. So I think there's a combination of things there. I think there is clearly computing power. There is clearly access to high-speed internet connections, whether that be 5G or whatever iteration of NBN or cable people might have. So can you make sense of that in some way, guys?
I'll have a crack at that if I may.
Thanks, Matt.
So, when you start looking at mill feed, and we do a lot of work around mill characterization, mill performance, recovery, etc. The key challenge has always been, we've been working our way through unpacking the easy puzzles to solve. So, for example, putting an IoT device on a truck to track it, get GPS data, put in wireless comms. Now we've got an ability to see what's going on. So we're slowly, incrementally digitalizing out the mining system. One of the key challenges as you move into ore handling or characterization is you've actually got to make sure you've got a really strong geomet model. So now what we're seeing coming in is the ability to do autonomous downhill drilling, ore classification, grading, etc. The challenge though is you then move, once you've blasted, you actually get mixing occurring. And that's actually one of the really hard problems that we've not been able to solve yet. And that gives us the whole challenge around mining, which is uncertainty. Now, as we move forward, we have a gap where we've blasted to the time it actually hits the crusher. So we've got to understand how we manage that problem. So we can do material tracking, but the ability to actually classify the ore and understand the ore characterization is actually a very hard challenge. We are seeing the ability to do in-situ blending and the ability to actually do grade classification using visualization techniques. So what the hypothesis is as we get better at being able to do visualization, and we're looking at using edge compute. So very much if you imagine the convoluted neural network that Els was talking about being applied to rusting, is actually what you can start doing with respect to classifying our ore. And you start looking at multiple different sample points. So visualization, real-time assaying, and there's all these other techniques. Now, the ability to then take that into the actual mill and understand what's going to happen in the mill is actually one of the key challenges that we are working towards. Now, what we're finding is, certainly with machine learning, is the ability to actually understand the classification, the material characterization, and the flow is actually giving us an ability to better manage the mill. And we're actually seeing more intelligent mill control. So that mine-to-mill problem is certainly beginning to be solved. And certainly some of the work that we've been doing in that space has had some phenomenal results.
And on that, so if you think about once you have all this information, typically you would put it into a METSIM model, but that runs hours. You can't use that type of model for an online process and real-time control. So here is where we look again at data science to kind of use our digital twins or emulators or what we want to call them to actually run real-time along with your control system, optimizing what you need to do without having to wait hours for a result.
And certainly what we're finding, and this is a great example of a system of systems problem. And so each one of those elements is a subsystem, and you actually daisy chain them together, create a golden thread, and that's very much how we're tackling that class of problem. And certainly what we're finding is you can then bring in additional information, so weather, so that goes to how clay might be, it's going to be wet. You bring it into mill control with respect to power draw, water, and you start building out a whole system effect. And that's really where it gets really exciting. And what we're also finding is the ability to do edge compute in that space is creating an amazing ability to solve that class of problem.
And Brendan, a final comment from my side. I think the other, from a concept perspective, in all the work that it's been shown today, and all the work that's been shown across the golden thread, every one of those steps can be extremely deep. Okay, we can go into in the mill area, you can be very deep with the level. At a lean concept, at a value stream mapping concept, we all know that a half balanced end-to-end value chain creates more optimization than optimizing one single silo to the nth degree. So at the end, one of the benefits that you get with this, the sort of stuff that we're talking about is the ability to be able to understand that what if we actually optimize one area much deeper than others, the actual benefit across the whole value chain. And so the capability is there to go deeper, the capability is there to ensure that we create the best overall value, and that the investment in innovation is actually poured towards the areas that are likely to give the overall best NPV. From a data science perspective, I think data is becoming cheaper. I think I'm not sure exactly the intent of the observation around 5G. Certainly the bandwidth is creating an ability to be able to handle more data faster. And like anything else, as organizations and as data scientists, we need to be balancing the compute cost and the bandwidth cost against the benefits that we're actually creating. So not ever should you be creating a false market, if that makes sense.
It does. It does. Look, guys, I think we're just approaching the hour mark, and I think you've answered quite a few questions there. And I just wanted to start wrapping up and thank all of you again for presenting today and for taking all those questions. I think there was a huge amount of value gained. I will just say to anyone that is going to watch this recording or is still online, please, if you have any further questions, you'll see both Matt and Rick's email addresses on there, or you can find them again through the optica.com.au website. So thank you very much, and thank you, Optica, for sponsoring today's content. We really appreciate it. Just wanted to say thanks to the three of you. Hopefully you find that you get a bit of engagement and a bit of interaction after today's session. And as I mentioned, we're also posting this recording across various social media channels and our Read Mining Events YouTube channel, which generally tends to generate quite a lot of interest as well. So any questions through those mediums, we will send through to you at a later date as well. So just wanted to finish off by saying the next webinar in this series will be broadcast on the 9th of July and will be with experts from Hastings Deering discussing asset production platforms and the theme of how data analytics can help improve productivity. So please join us in a few weeks for that one. Thank you to everyone who joined us today. We really appreciate you giving up your time to listen to the experts today. And we hope you can join us again soon. That concludes today's session. Thank you very much.
Thank you.
Thank you.
Thank you.